organisms that have biological processes, reproduction, energy consumption. Nice, yeah, those are all great. And I think I mentioned this to one group, sorry, for people who just rejoined, I asked what people were looking at as a definition for life. So we have two in the chat, capacity for change, as well as biological processes like reproduction and energy consumption. And one thing that's really interesting is that how an astronomer defines life is going to be different than how a biologist defines life, because we want a very, very, very broad definition. So for astronomers, when we talk about life, anything with the ability to replicate itself, we're going to consider to be alive. So this is where kind of the big thing that's a little fuzzy is, especially I have a friend who's a biology professor, and we will argue about whether or not viruses are alive, because viruses can replicate each other. They're really good at that. But most biologists don't necessarily think viruses are alive. So a biologist might say that life requires DNA and RNA, but then there are some bacteria that only have DNA or only have RNA, so that doesn't work there either. So we're going to focus on this ability to replicate itself. The idea of some form of growth and change is also often important for life, so life has to be able to grow and change. And then also the other big one is going to be life needs to consume some sort of energy. So there needs to be some sort of, energy consumption process that happens for it to be considered life. Kind of similar along the lines of DNA and RNA, we can think about life as anything that utilizes amino acid. It's in the form of proteins to do this fueling, to have this energy consumption. So amino acids are just, this is where I am an astronomer, my biology knowledge is very low, but amino acids are organic compounds that we have seen on some meteors, which is kind of interesting. So they're chains of proteins, and there's some signs that maybe these building blocks from life came from an interstellar source. But there's also reason to believe that that just already was on Earth too. If it's in meteors, there's no reason that it wouldn't have formed with Earth. So kind of one of my big takeaways from this talk. Are there aliens out there? Almost definitely yes. Have those aliens visited Earth? Almost definitely no. I do not believe that aliens started life on Earth, but I do really think there are aliens out there. And there are some interesting theories about meteors bringing amino acids to Earth. I don't really know. But yeah, so the main thing to take away is that life, the way we're going to define it as astronomers, is it's something that can replicate itself, something that can reproduce in some form or another. So then, okay, you guys already did this step, but if we're looking for life, what did you guys think? What are the conditions necessary for life to exist on a planet? So this is another one. Shout out, put in the chat. What do we need for life to exist? Water, water's a big one. Atmosphere, definitely. Anything else? The right temperature, yeah. So that's going to have to do with there being liquid water. We want to be somewhere where the temperature is right that we can have liquid water. So definitely. Oxygen, yeah. So actually, we'll talk about this too, but we specifically look for some specific types of organic molecules. Oxygen is one of them. Not competing for resources, yeah. So making sure that, we have a big enough space for different life to exist without having to fight each other for the energy sources out there. So all good. And just like you guys all started with, the first and most important thing we think about when we look for life is we look for places that have very specifically liquid water. So I talked with one group that we know the moon, we know Mars has solid water, has ice, but that doesn't necessarily mean, but what we need for life to exist is liquid water really specifically. And that's because we're pretty sure life requires a solvent. So a material that you can dump your organic compounds in and have them mix around and potentially stick together and form something bigger. So some sort of liquid is important. We think water is a really great liquid for forming life for a few reasons. The main one is that it's a dipole. So little dose of chemistry. When we have water, water is dihydrogen monoxide, so H2O, 2 hydrogens and 1 oxygen molecule. When they stick together, when they form their bonds, it ends up being the oxygen is slightly more negatively charged and the hydrogens end up being slightly more positively charged. So just based on the way they share electrons, we get a slight positive charge on the hydrogen end and a slight negative charge on the oxygen end. So that's what it means when we say water is a dipole. And water being a dipole makes it really easy to dissolve different materials in water. So almost anything will dissolve in water eventually. So like think if you add salt to water and you mix it up, you don't just have a bunch of salt grains on the bottom, you actually have salt water. Same with like sugar, anything else, anything you put in water, for the most part, especially these organic compounds, will dissolve eventually. And this is good again for life because we want to mix these components together somehow to get things to stick, form those amino acids, form bigger things that could eventually become life. So having a solvent that is a dipole, good. Water is also really ideal because its solid form is less dense than its liquid form. So, okay, what do I mean by this? If you think about having a water bottle and maybe you go skiing and you have your water bottle with you and all the water freezes and your water bottle cracks because the ice form of water, the frozen form of water, is less dense. It gets bigger when it freezes instead of getting smaller when it freezes. Water is really unusual in this way. Not much else does this. And why this makes it a really nice solvent is it means that if your water freezes, you get, if you have like a frozen lake, there's going to be ice on the top layer first. The ice will float. So it freezes from the top down instead of most other materials, which will freeze from the bottom up. And that's good if you're a fish, because it means that as the water freezes, you still have a nice, safe place to hang out away from predators as it freezes from the top. And it means that when spring comes around again, it's really easy to melt that surface layer and get your water back to being liquid again and not end up with a constantly frozen bottom part of your pond. So water is great. It is a good solvent. It is a dipole, which allows it to mix things together. And its solid form is less dense than its liquid form, which means it freezes from the top down. Liquid water is also good because it flows. This is true for any liquid really, but if you get something flowing, that's good if you want to bring nutrients in or take nutrients out, or take waste out, I should say. We want the nutrients to come in. So if you think about like, if you've ever run tide pooling and you see the barnacles reaching out, they can just sit in their tide pool and have food brought to them. They don't necessarily have to move because water is flowing. So this is great for life. It can bring nutrients in, take waste out. So water is good for eating and it is good for pooping if you are a young organism. So water is great for all of these reasons, and it's why we think there is life on Earth, is because we exist at the really nice temperature and pressure conditions where liquid, solid, and water vapor can all exist pretty easily. So ice, water, and steam can all happen in our atmosphere because we are around the triple point for water where all those three phases are possible for existing. Based on all of this data and the fact that right now we only know of one planet with life, we think water is pretty essential for life to form. That being said, it's possible that we don't need water as long as you have some form of liquid. So we don't know, but we do have an example of a place in our solar system where there are liquid methane and ethane lakes. And there is a possibility that you could get life forming the same way that we have life on Earth that forms initially in our oceans. Maybe in these ethane and methane lakes on Saturn's moon Titan, we could get a different form of life developing. It's not as ideal. It doesn't have those same nice properties as water, but it still flows and it still is a solvent where we can mix together these organic materials. So maybe not the best solvent, but there's a possibility that you don't need water if you have some other form of solvent. We don't know though. So that's our first one, is water. Any questions about any of that? We'll talk more about Titan later, I promise. So this one, next one, I'm not sure anyone said this specifically, but I think we kind of hinted at it in a few ways. So the next big thing any form of life is going to need is a source of energy. So this gets back to life needing to consume, eat somehow to survive. So we need energy to reproduce, we need energy to move around. So there needs to be some form of energy in order for us to get life. So on Earth, that energy source is primarily the sun. I know that we don't photosynthesize, but we eat things that photosynthesize, or just eat things that photosynthesize, depending on what your diet is. So even if you're eating a cheeseburger, that cheeseburger used to be plants. Those plants got their energy from the sun. So most of the things we see on Earth, you can kind of trace back where they're getting their energy to the sun. There's a few exceptions to that. But for the most part, we're getting our energy for the sun. So what this means is we need our planets, if we're looking for life, we need them to be close enough to their star or some other source of energy that we think that there's a source of energy for life to sustain itself, that we can either get that through photosynthesis or other forms of redox chemistry. So it's another, I'm an astronomer, I am not a chemist, but we have found some forms of life, some extremophiles on Earth, either at the bottom of the ocean where there is little to no sunlight, or in caves where there is definitely no sunlight, that do seem to exist without energy from the sun. They primarily do this through chemosynthesis, sorry, I cannot say that word, where they're turning hydrogen sulfides into energy through chemical reactions. So there are some examples of life on Earth that do not need sunlight, but you still need some form of energy, whether that's chemical energy, geothermal energy, the life that's around geothermal vents at the bottom of the ocean. So you can get life from geothermal energy, or most of life on Earth, we're getting energy from the sun. So far we have two requirements: water, or at least some sort of liquid, and a source of energy. The next one, this kind of gets at what Maddie put in the chat. We need to make sure we're on a planet where there's nothing that's going to destroy life. So whether that's competing for resources, or as this image shows, we do not want to be on a planet where our star is very, very active. So we don't want to be somewhere where there's a lot of coronal mass ejections, because that could harm life. So this kind of rules out, we probably aren't going to find life around O stars that don't live very long before they go supernova. So probably not O stars, and also probably not red dwarf stars, because red dwarf stars tend to be very, very active. So that activity could, in theory, wipe out life pretty easily. So nothing that will destroy life. So we have water, an energy source, and an energy source that won't kill you very, very quickly. So far. The next one, this is one Emily said that we will probably need an atmosphere. So this is exactly true. We think, again, don't necessarily know. We have one example of life. So we're kind of statistical sample of one. It's not a great sample set. But what we think is that you need an atmosphere to protect your planet from harmful radiation, as well as allow for temperature to be moderate, and hold on to the organic compounds like oxygen that we think might be necessary to start life. So our atmosphere does a great job of blocking a lot of the UV radiation that could be harmful for life on Earth. It also blocks some galactic cosmic rays that could be harmful to life on Earth. So this protective layer of oxygen, nitrogen kind of keeps us safe from some of the harmful interstellar and stellar radiation. Also gives a mixing area, so the water gives a mixing area, but also where our atmosphere holds in compounds that we think we need to get life started. So those amino acids and other organic molecules we think are necessary for life. And then also, you know, you don't want to be on Mercury where you don't really have an atmosphere and you're alternating between like temperatures of 900 degrees and 100 degrees. It's going to be hard to get life started there. So we want an atmosphere that allows temperature conditions to be relatively stable, where we're holding in heat and keeping that sunlight, that energy source that comes through, we're keeping some of that heat inside of our atmosphere. On the other hand, we don't really want to end up like Venus either. We don't want too much atmosphere because that'll make the pressure and temperature conditions extreme, and that also is not great. And kind of a little side note, at the beginning of this semester-ish, there was discovery of phosphine on Venus that suggested there might be life there. Since then, we've found that that was probably not real. So that was probably a mistake. Other groups have tried to replicate this measurement and they haven't detected phosphine. So we're thinking that there probably isn't phosphine on Venus's atmosphere. So we should still explore Venus and figure out what's going on there. Seems unlikely that there's going to be life. Sorry. No penguins pooping on Venus. Okay. So our next thing, second to last, I think, are the schnapps. So these are our organic molecules that seem to form all of life on Earth. So schnapps stands for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And it's fun to say. And they seem to be the 6 elements that are in any form of life on Earth. So when you guys did the We Are Made of Star Stuff activity, you saw that us humans are mostly oxygen, carbon, and hydrogen with some of this nitrogen, phosphorus, and sulfur and other heavier elements. But this just seems to be the building blocks for life. DNA, RNA, these proteins are all just chains of these different elements for the most part. Again, because we only have a sample of Earth, this is what we are working with. We are thinking that life, it must be formed out of these things. It's possible that if you had life on another planet, it could form out of lithium, beryllium, and sodium. We don't really know, but it just seems like, based on what we see, that even different forms of life, even the extremophiles we measure on Earth, still seem to be mostly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So the things that are living in caves and never see the sun still consume energy through hydrogen and sulfur, and they still seem to be primarily made out of carbon. So besides all life on Earth is formed with schnapps, we don't have a good reason for saying we need these, but again, it's what we know, and so it's what we think we should look for if we want to find life on another planet. And you're going to need to build life out of something. These seem like fairly good building blocks for life. Okay, so let's see if I can get through all of them. So we had water, a source of energy, nothing that will destroy life quickly, an atmosphere, sorry, and then our schnapps, our organic molecules, are big things that we think we need for life. Any questions on any of that? With a lot of caveats thrown in that we don't know anything. So this is my favorite part of this, is now thinking about, we will talk about exoplanets, but I think it's more fun to think about where there might be life in our solar system, specifically because these are the places where we, in theory, could actually get to. Right now, we have found planets around the nearest star, but that nearest star besides the sun, sorry, nearest star besides the sun, but that star is 4.3 light years away. So even if we could travel at the speed of light, it would take us 4 years to get there, which we can't, and that is a long time. So thinking about where we might find life in our own solar system first is kind of very exciting, in my opinion, and I think we should be focused on that for now. So there's a few things to think about. They're kind of, first we want to think about the planets. Are there any planets that might have life besides Earth? At the moment, it seems like the answer to that is no. When we look at the terrestrial planets, there aren't any that currently have stable liquid water. Mars used to have liquid water. We are pretty much 100% certain about that, but it does not seem to have liquid water anymore. So we don't think there's any possibility that there is currently life on Mars. Based on everything that the rovers have found, we haven't seen life. It seems unlikely that it's there. There's some joke that Mars is the only planet we know of that is entirely inhabited by robots because of 3 rovers. So technically true, based on what we know. We don't think there are aliens. There are 3 rovers. The detection of phosphine on Venus was cool, but it seems like it was a kind of false alarm, and there doesn't seem to be life there. And then Mercury and our own moon are just not, they don't have atmospheres. They don't seem to have conditions for stable liquid water. It's very unlikely we would see any life on the giant planets because there are no liquids at all, except for liquid metallic hydrogen. But that's weird, and we don't think that's a good situation for life. So the giant planets themselves are not great candidates for life, but there are some really cool moons around Jupiter, Saturn, Uranus, and Neptune. All of them have cool moons. I'm going to run through a few of them that might be really good candidates for places with life. So I'm going to start with Jupiter, then look at some of the moons of Saturn, and then I think I have 1 moon for Neptune. A lot of these are going to be kind of repetitive, so I'm going to try to hit some of the exciting things, but not spend too long saying the same thing over and over and over again. So the first moon of Jupiter, of the 4 big moons of Jupiter, is Io. Jupiter has something like 60 or 70 moons. I don't know what the number is right now, so I'm only going to pull out 4 of them. But Io is the closest moon to Jupiter. We don't really think it has life, but it's kind of looks like a pizza and is cool, so I wanted to mention it. It has a lot of volcanic activity because it's actually being stretched by tidal forces from Jupiter. So it's close enough to Jupiter that just like the moon causes tides on Earth, Jupiter is actually squishing the rocks on Io and turning them molten and making all of these volcanoes. Because of this, and also because it doesn't seem to have water, Io is not a very great candidate for life. It also has the issue that it seems to be moving through a ring of charged particles trapped in Jupiter's magnetic field, which could be one of those things that could kill life. So Io is not great, but when we're talking about moons of Jupiter, you have to throw it in there because it's one of the 4 main big moons that people talk about. On the other hand, Europa, the next big moon of Jupiter, is a great candidate for a place where there might be life in our solar system. So Europa is one of these, we're going to talk a lot about these icy moons. These are moons that seem to have a layer of ice over a layer of liquid water. So these moons that have these giant subsurface oceans. Again, Europa experiences tidal heating, which causes so we see the surface of Europa seems to be ice. We've measured this surface. We're pretty sure that the surface of Europa is all water ice based on its color and spectra. And we can also see that the surface of Europa has a lot of cracks on it. So we can see these cracks in this image and also on this image of the total planet of Europa. There are these big cracks, which tell us that the surface layer of ice is shifting over this water surface, and those cracks will let in sunlight. So there is sunlight coming in through these cracks, providing that source of energy. The fact that the surface is cracked again tells us there's liquid water, which tells us there's some tidal heating warming up that water too. There's a really good chance there's also geothermal vents at the bottom of this ocean. So hydrothermal vents, just like on Earth, at this bottom of this ocean on Europa. Because of this, there is actually a NASA mission. So on next Tuesday, we will talk about NASA missions. One of them is the Europa Clipper, which is scheduled to launch and head to Europa and look for life in 2022. So very good candidate for life in our own solar system. There's also a fun movie called Europa Report about a group of astronauts who go to Europa to look for life. And it's fairly accurate until they actually find aliens, and the aliens aren't exactly what we would expect. If we find life on Europa, it's probably similar to what we see around geothermal, hydrothermal vents at the bottom of our ocean. Mostly bacteria, potentially some things that look sort of like weird plants. Similar to Europa is Ganymede. Ganymede is the largest moon in our solar system. It's also a moon of Jupiter. Similar to Europa, we have a layer of ice above a layer of liquid water. Also heated by tidal forces, also has a cracked surface. So we can think of this even kind of similar to tectonic plates on Earth. We have these giant sheets of ice moving across this liquid ocean. And again, the cracks that we see on the surface of Ganymede suggest that there is energy getting through into this layer, into this ocean layer underneath it. So what we think is going on in Ganymede is we have a layer of ice over a saltwater ocean surrounded by a liquid core similar to what we see on Earth. So another cool potential life place. And the last one of Jupiter's moons, again, very similar, is Callisto. Also has an ice surface, but it's slightly further away. Europa is the closest one. This is why we send things to Europa, is because we can definitely tell it has an internal heat source, probably mostly tidal. So it has more of that energy source than the other moons. But Callisto also has a little bit of an internal heat source. Also, we see some cracking along its surface, just less. So still has this subsurface ocean. We could still get some microbial life that is potentially eating hydrogen sulfides from hydrothermal vents. We don't really know, but it seems maybe slightly less likely than Europa. So those are the moons of Jupiter, where we think there might be life, or on Io's case, probably not. Any questions about those? Not hearing anything. So now we're going to move to moons of Saturn. The first moon of Saturn I want to mention is Titan. Titan is Saturn's largest moon, second largest moon in the solar system. Not too different in size from Earth, so it's smaller than Earth, but not bad. And like I said earlier, we have found that Cassini, one of mission 2, Saturn actually landed a probe on Titan, and we saw that it had liquid methane and ethane lakes, where in theory you could develop life. So there's a solvent, it's not water, but maybe you don't need water as long as you have some form of liquid. It has a bit of an atmosphere as well. It's cool enough that even though it's smaller than Earth, it can still maintain its atmosphere. And right now there are scientists on Earth that are trying to replicate the conditions on Titan to try to see if they could get life to develop. I think as of yet, we don't have a conclusive answer, but it's kind of hard to get a conclusive answer on this because we don't exactly know what sparks life. So we have an idea of what life is, sort of, but we don't know how life started on Earth besides in the ocean. So like if there was some specific event that started life, like we don't really know. So we're trying to see if we can recreate the conditions in Titan, and if you leave that for long enough, does life happen? But we haven't seen it yet. Saturn also has my favorite moon, which is Enceladus. So I think Enceladus is probably, if I had to pick if I could send something anywhere, I would send it to Enceladus because I think Enceladus is really cool. But this is a smaller moon of Saturn. Similar to Europa and Ganymede, it seems to be an icy moon with a subsurface ocean. We see a lot of these cracks that tell us that there is liquid water underneath the ice surface. But the other thing that's very, very, very cool about Enceladus is it has these huge ice geysers. So they're sometimes called cryovolcanism, or like ice volcanoes, where we're actually spewing snow out into the atmosphere around Titan, or Enceladus, sorry. And the reason why this is so exciting is, first of all, it tells us that the water underneath this layer of ice is pretty warm. It's warm enough that it's heated and pushed out like geysers in Yellowstone. Like those are really hot, and that's how you get the energy necessary to actually force this water up. So there is a heat source inside of Enceladus. Might just be tidal heating from Saturn, but there's an energy source in Enceladus. We could definitely get life there. And the other thing that's really cool about it is you don't necessarily have to land on Enceladus to sample the liquid ocean underneath it. You just have to fly through those geyser jets, and you could, in theory, see if there are organic molecules there that might suggest there's life underneath the surface. I think Enceladus is super, super neat. Other things that make it cool, it's got this area in the southern hemisphere that's showing down here, this image here. That's called the tiger stripes, because they think these cracks look sort of like tiger stripes. So that's cool too. And yeah, I just think Enceladus is awesome. The other thing to think about that is, even if we didn't find life if we went to Enceladus or Europa and we didn't find life, that could be extremely interesting too. Because in theory, these moons have the exact same conditions as hydrothermal vents in our ocean. So why would we get life around those and not life on these moons? So that is an interesting question in and of itself. So not finding life would also be really cool and tell us a lot about what we need in order to get life to form. But it would also be, there's also a possibility that there just are little tardigrades or something swimming around underneath the ice in Enceladus, which would be really, really cool. A few other just quick hits in Saturn's moon. I have to always show a picture of Mimas because it looks like the Death Star. So you've got your big crater there. This is not a Death Star, though it is a moon. So it's one of the small moons of Saturn. Could also have a subsurface ocean, but doesn't have those nice crack features that suggest energy getting down to the subsurface ocean. So probably not a good candidate for life, but a good picture to show your friends if you want to tell them that there's a Death Star around Saturn. Another one I throw in a little bit more for cultural reasons is Iapetus, which is also, we think of it as Saturn's yin-yang moon, because it has a dark side and a light side. So there's one side that seems to be really covered in dust, and one side that seems to be really, really white and bright and covered in ice. Potentially this ice is from Enceladus, so Enceladus is spraying out ice, and maybe some of it's landing on Iapetus. So probably not a great candidate for life, but if you have read 2001: A Space Odyssey by Arthur C. Clarke, the reason they are traveling out to, I think in the movie they go to Jupiter, in the book they go to Saturn, but it's because they're seeing this flashing signal from Iapetus of dark, bright, dark, bright, dark, bright, that tells them to travel into space. So if you are an Arthur C. Clarke fan, maybe you want to argue that Iapetus is a signal from the aliens telling us to venture into space, but probably doesn't actually have alien life. My last moon is a Triton, which is an icy moon of Neptune. So again, very, very similar. Cracks indicate we have subsurface liquid water that is getting energy from the sun. The cool thing about Triton is that we've detected carbon dioxide in the atmosphere of Triton. The issue with Triton is Neptune is a lot further from the sun than even Jupiter and Saturn. So it's not, even if these cracks are letting sunlight in, it's not getting a lot of sunlight. So you probably need some or there's other source of energy if you want to be life on Triton. So cool moon also has water, but probably not the best case for life in our solar system. So that was just a lot of little fast facts about all the fun moons out around our giant planets. Before we talk a little bit about exoplanets, does anyone have any questions about any of those? So the last place we can think about looking for aliens is on planets around other solar systems. We have found in the past something like 30 years, we have found 5,747 exoplanets. I checked this morning and that's what the number was, so probably is still true, but could have gone up since then. And this is just a graph that I made this morning also showing the mass of those planets versus the distance they are from the sun. So this is in masses of Jupiter. So Jupiter would be somewhere out here. Earth would be kind of down in this area around 1 AU. So we're 1 AU from our sun, and we are much smaller than Jupiter. So we're kind of down in this area. So we haven't detected a ton of planets that look exactly like Earth, mainly because Earth is very hard to detect. We are small and we're pretty far from our sun, or kind of far from our sun. So that just makes it slightly difficult to see planets like Earth. The two methods for detecting planets I want to talk about really briefly are the transit method and the radial velocity method. So on this graph, I think red is planets that were detected with the transit method, blue is the radial velocity. So most of the planets we have detected are with these two methods. The green and the yellow are microlensing, which is complicated and I don't want to dig into it, and then actual imaging of planets. So there's a few planets where we have actually gotten an image of the planet themselves, which I think are these yellow points up here. For the most part, that's really hard to do because you need a very big planet that is far enough from its star that you just don't get completely overwhelmed by starlight when you look towards it. So the transit method, on the other hand, uses the changes in the brightness of stars to find planets. So as a planet travels between us and its star, it will block a small amount of light from that star. And if we see this periodic dimming, if we can see dips like this that occur regularly over time, that tells us that there's going to be a planet around that star. The Kepler space mission, which we'll talk about when we talk about NASA missions, looked specifically for these dips in brightnesses around stars. And with these dips, it found thousands and thousands of planets, which is really cool. The other nice thing about the transit method is the timing of the dips tells us the period of the exoplanet. So we see a dip once every year for that planet, so we can get an idea of what the period is, which if we know what kind of star it is, that can tell us using Kepler's law, we can find the semi-major axis, so the distance between the planet and the star. And then the depth of the dip tells us how much light the planet is blocking. So bigger planets will block more light. So the transit method, we get the separation between the planet and the star, and we also get the size of the planet. So you get quite a bit of information just by watching these transits. There's also work being done to try to measure the spectra that we see from these transiting exoplanets to try to see if they have any of those schnapps in their atmosphere. So do they have organic molecules in the atmosphere of these exoplanets? The other method, again, just gonna mention briefly, is the radial velocity method. And so this is something we can do from Earth. Transit method, you pretty much have to do from space, but we're getting better. We can sort of do it from Earth now. And radial velocity uses Doppler shifting to measure the presence of a planet. So when we have a planet orbiting around a star, what's actually happening is the planet and the star are orbiting around the combined center of mass of the two systems. So for the Earth and the Sun, the combined center of mass for the Earth and the Sun is inside the Sun. So the Sun isn't moving much, but it is shifting back and forth a little bit as we orbit around it. And this is true for every exoplanet too. And if we can observe Doppler shifts in the spectra of these stars, we can tell if we see they're periodic, we can tell that the star is moving slightly forward, towards and away from us, towards and away from us. And that tugging might be because it has a big planet orbiting around it as well. The nice thing about radial velocity, so again, we get a period. If we know the kind of star, we can use Kepler's law to get a semi-major axis. We can try to get a mass based on how much this shift is happening. So that'll tell us a bit about what we think the mass should be. So we can get masses and semi-major axis of these planets based on the radial velocity method. The other nice thing is the transit method. You need the planet to pass directly between us and the star. The radial velocity method, that doesn't necessarily have to be true. We will still see these kind of shifts, even if they're not directly aligned, so the planet isn't exactly blocking the light from the star. The last thing that's really cool is that it can be done from Earth. So the spectrograph telescopes we have on Earth can actually do this, whereas a lot of the transit method, for the most part, we have had to do from space to remove effects from our atmosphere. So those are my two methods for detecting exoplanets. If you want to use the transit method to detect an exoplanet yourself, you can do the exoplanet lab, which I think is our last lab for this section, and see what these transits look like and how we can pull out some of this information about exoplanets from them. So whether or not there's life on exoplanets is kind of hard for us to say. We know there are a bunch of them. So like I said, we've detected 5,000, over 5,000, almost 6,000. And that's only looking at a few stars, or thousands of stars, but not looking at all the stars in our galaxy. So we know there are probably billions of exoplanets in our galaxy alone. So the idea that there's only one planet in our galaxy that has life seems kind of insane with those statistics. So there's probably life on a exoplanet. The problem is whether or not we will ever know, hard to say. We can't get to an exoplanet. Even the closest ones are light years away. We do not have a method to travel to them at this point in time. Maybe sometime in the future. Right now, it's not really an option. Instead, what we can do is we can look for signatures of life in their atmosphere. So look for those organic molecules by taking the spectra of these stars as these planets as they transit their star, and looking for changes that suggest there might be water or other different types of atmospheres around these exoplanets. We have found quite a few Earth-like planets through Kepler's transit searches. So these are just a few that we've found so far. And specifically, when we look for habitable planets with Kepler, we're looking for planets that are in the habitable zone. So this is what you guys said, the first most important thing we look for life, or we think life needs, is liquid water. So the habitable zone is kind of the area around a star where the temperature conditions are right for liquid water to exist. So for stars like the Sun, that will be 1 AU away. For smaller stars, that's going to be closer. For bigger, brighter stars, that's going to be farther than 1 AU away. So depending on what type of star you are, your habitable zone will grow or shrink. It's just going to be the area around that star where liquid water could exist. So last thing I want to talk about is a few little ways that we actually search for extraterrestrial life, and then I will let you finish up that activity, and that's how we'll end. So the big one is SETI. SETI is the Search for Extraterrestrial Intelligence. And it's this big dish in Chile that is looking for signals that could suggest life in the radio. So if you have seen Contact, the movie Contact, this is based around SETI, the woman who helped found SETI. It's Carl Sagan and his wife, Anne Duran, I think, are the main founders. So Contact is about Andorian's life, sort of fictionalized, where there are aliens, but it's also a good movie with aliens in it. And we think that looking in the radio might be good because we can find patterns that might be similar to the patterns that electronics on Earth are making. And that could suggest intelligent civilization somewhere else in our galaxy. And just briefly why we look in the radio, and that's because life is, or intelligent life, communicating intelligent life seems to be pretty bright in the radio. So if you look at our solar system, Earth is going to be the brightest in the radio of everything. So it's actually brighter than the sun. And that is because we are emitting a ton of radio waves. So through television broadcasts, GPS satellites, radio, actual radio, if you use that anymore, all of these things are emitting radio waves. And those are just traveling, they're traveling around Earth, but they're also traveling out into space. So for the past 100 years, we have been emitting radio waves into space. I really like thinking in Futurama. I like Futurama, if you can't tell from this. But there's a joke that the aliens at Omicron Persei 8 are 10,000 light years away. So they're watching television from Earth 10,000 years in the past because they're just getting that signal. That is possible. It's possible there are aliens 100 light years away that are getting our first radio broadcasts right now. Radio light is also great because it can pass through, it's really long wavelength, so it can pass through dust in our galaxy without being absorbed or scattered. And when we send out, like I said, we send out signals in the radio. So we think if there are other intelligent forms of life out there and they could communicate with us, the best method for them to communicate with us is going to be in the radio. We don't know. It is possible there are other ways for communicating life to work, but we have, like I said, we have one example and it's us, and we are extremely bright in the radio. And we send out regular kind of emissions that we think might be a signal that we could look for life on other planets. Okay, so I'm going to end with the Drake equation, but before I do, does anyone have any questions on any of this? Okay. So last thing, don't worry about trying to write all this down. This is kind of a big thing, but I always like to end when I talk about aliens with talking about the Drake equation. So the Drake equation is something Francis Drake, I think, came up with. I think maybe that's not his first name, sorry. But it's this way of trying to predict the number of technologically advanced civilizations in the Milky Way galaxy. So only in our galaxy. We're not even considering whether or not we can communicate with aliens in other galaxies. That's too hard. And so what this is it's how many stars are in our galaxy, what fraction of those stars have planets. Right now, we think there are about 10 billion or so stars in our galaxy, and we think pretty much all of them seem to have planets. Pretty much every time we look at a star, we have found a planet if we are looking for a planet. So this is close to 1, this is close to 10 billion. So right now we have a big number. Then we multiply it by the number of planets in a planetary system that seem to be suitable for life. So this is where we start getting a little bit more tricky, and where we don't necessarily know these numbers very well. So how many of your planets, how many planets are typically around a star? How many of those planets seem to be in the habitable zone, have those conditions where we could get liquid water? Then of those planets, what fraction of them develop life? This is where we have no idea, because we have one example, we have 1 out of 1, a planet in a habitable zone developed life. So potentially it's as high as 100%. Could be a lot lower though, we really don't know. So then of those planets that develop life, what fraction of those planets develop intelligent life? So what fraction of those planets with life get to intelligence? what fraction of those intelligent life forms get to the point where they can communicate with another civilization, so start broadcasting in the radio. And then the last number here, L, is the length of time that that civilization will be sending out detectable signals. So for us, that's been about 100 years. If we continue on for longer, it could get a lot longer, but we don't know what this number is. So this is just an equation that, like I said, Dr. Drake, his first name, sorry, wrote to try to predict how many intelligent communicating life forms could be in our galaxy. Depending on what numbers you use, you can get anything from 1 to 5,000. We don't know. So we might be alone in our galaxy, but that's pretty unlikely. It's also possible that there are 5,000 other communicating civilizations in our galaxy. Whether or not we ever talk with one, it's hard to say. But it's kind of a fun way to try to guess at how many other alien species could be out there. So now that you have heard me talk about aliens, you should have enough information to answer questions